let's pull back the curtain on an invisible architecture that honestly shapes our entire digital lives. It's this fundamental language you probably don't see, but I promise you, you use it every single day.
So think about this for a second. What's the common thread that connects your Netflix recommendations, the way a character moves in a 3D world, and how a search engine can rank billions of pages in an instant? Now you might think, oh, it's just really clever coding. But the real secret? It lies in the mathematical DNA that's hiding just underneath it all.
The answer is a secret language. And no, I'm not talking about Python or Java or anything like that. This is a mathematical language, a whole framework for thinking about space and data and transformation that has become the absolute bedrock of modern technology.
That language is linear algebra. And look, before you get scared off by the name, I want you to think of it less like a scary math class and more like learning the grammar of a new language, one that describes systems, relationships, and the very geometry of data itself.
So, the most basic words in this language, you can think of them as the nouns, are called vectors. Geometrically, just picture an arrow pointing from a starting point to a specific spot in space. That's it. In practical terms, it's just an ordered list of numbers. For instance, a vector could represent your ratings for 3 different movies, pointing to a unique spot in what we could call movie space.
Okay, so if vectors are the nouns, then matrices, well, they're the verbs. They are the action words. See, a matrix isn't just some boring grid of numbers. It's a transformation machine. When you apply a matrix to a vector, it literally moves that vector. It can stretch it, shrink it, rotate it, or even flip it. And believe it or not, this one simple idea is the key to everything from 3D graphics to data analysis.
All right, so now we have our nouns, the vectors, and our verbs, the matrices. We can start forming sentences to solve some really interesting problems. And the most elegant way to do this isn't to get bogged down in individual numbers, but to start thinking in terms of entire spaces.
This is it, right here. The central puzzle, the absolute heart of linear algebra, boils down to this one beautiful equation. A times x equals b. So, A is our matrix, our transformation machine. X is some unknown vector that we're trying to find. And b is our target vector, the place we want to end up. The whole question is, what input vector x can our machine A transform to land exactly on our target B?
Now there are 2 ways you can visualize this puzzle. The traditional row picture sees each equation as a line or a plane. And the solution is that one tiny point where they all intersect. And it works, but it can be kind of hard to picture. But the column picture, this is where things get really powerful. It asks a totally different question. How can we combine the columns of our matrix A, treating them as vectors, to land exactly on our target B? This completely reframes the problem as a journey, finding the perfect recipe of ingredients to create the exact result we want.
So, how do we find that perfect recipe? How do we actually solve for x? Thankfully, we don't have to just guess. Linear algebra gives us this beautifully systematic process for finding the answer every single time.
This process is called elimination, and its whole goal is just one thing: simplification. You start with what looks like a big, messy system of equations, but the genius of the method is that you can strategically combine the equations to cancel out or eliminate variables. You keep doing this until you get this clean, staircase-like structure. The very last equation has only one unknown, which is super easy to solve. And then you just work your way back up the staircase, plugging in the values you find. It's literally a method for turning chaos into order.
Solving for x is useful, for sure. But the true power of this language comes from understanding the deeper properties of the transformations themselves. Like, what is a matrix really doing to the space it's acting on?
This brings us to a really beautiful and powerful concept, the eigenvector. It turns out, for any given matrix, there are these special secret vectors that when they get transformed, don't change their direction at all. They might get longer or shorter, but they stay pointed along the exact same line. These vectors are the eigenvectors, and they reveal the stable axes of the transformation, the directions where all the action is just pure stretching or shrinking.
Think of it this way. If a matrix is some complex transformation that twists and turns and warps space, the eigenvectors are its skeleton. They provide the underlying structure. As soon as you understand a matrix's eigenvectors, you understand its fundamental behavior. You know what it's really doing deep down. Okay, so we've got our nouns, our verbs, and now this idea of a transformations skeleton. So how does this abstract language actually power all that technology we talked about at the beginning? Let's see it in action.
This is where it all clicks into place. Rotating a character in a video game?
That's a matrix transformation, plain and simple. Google's original, game-changing PageRank algorithm, it worked by finding the most important eigenvector of the entire internet to figure out which pages mattered most. Compressing a huge photo into a tiny JPEG file, that uses a technique that breaks the image's matrix down into its most essential components and then just throws away the less important stuff. In every single one of these cases, the solution is pure, beautiful linear algebra. The elegance is just undeniable.
So, ultimately, linear algebra is this silent, organizing principle behind so much of our digital world. It's the ghost in the machine, a hidden framework that gives us the tools to manipulate data, model incredibly complex systems, and transform space itself in ways that are predictable and incredibly powerful. And hey, this isn't just about high-tech stuff. This language is spoken in economics, in statistics, in physics, in engineering. Once you start to recognize the grammar, vectors, transformations, systems of equations, you start seeing it absolutely everywhere. So the next time a movie recommendation pops up, you'll know about the hidden language at work. Now that you can see it, where else are you going to find it hiding in plain sight?